Next topic in covalent bonding chapter is valence shell electron pair repulsion theory, which is abbreviated as VSEPR, that is Vesper's theory. Now points of this theory are shape of molecule if there are two atoms only. If two atoms are there, the shape of that molecule will always be linear. And if molecule contain three atoms or more than three atoms or more atoms are there, then one of the atom is called the central atom, and to this the other atoms they will link. If central atom, this has only bond pairs around it. There are only bond pairs around this thing. Then repulsion from all sides will be similar. And the shape of this molecule will be symmetrical shape. The shape of the molecule will be symmetrical, or we'll say this has regular geometry. Geometry means shape. Regular shape of the molecule if there are only bond pairs around central atom. But if along with the bond pairs there are lone pairs also around the central atom, then from all sides the repulsions will not be same, they will be different. Central atom, like for example, these are the bond pairs and here this side is a lone pair, then repulsions will not be same. Then the molecule will have irregular geometry, or we'll say the geometry of this molecule is distorted. The order of repulsion between electron pairs is more repulsion is between lone pair and lone pairs, then the repulsion is between the lone pair and bond pair, and very less repulsion is between the bond pair and bond pair. Because of the lone pairs, the repulsion order will not be same. But if only bond pairs are there, then repulsions from all sides will be the similar. And exact shape of the molecule will decide from this thing. Exact shape of molecule, it depends upon the total number of electron pairs around central atom. How many electron pairs? Electron pairs means bond pairs plus lone pairs are called electron pairs. How many total electron pairs are there? How many are bond pair from this? How many are the lone pair from this thing? From that will decide the geometry of the molecule. So for this we have a table to learn this thing, that if these many bond pairs are there in a molecule, what will be its geometry? If along with this the lone pairs will come, what will be the geometry of the molecule? So now next we are doing the table for Vesper theory. First column I am taking total number of electron pairs. Then out of these electron pairs, how many are bond pairs? How many are lone pairs? Knowing the lone pair and bond pair, we will decide the geometry or the shape of molecule we can decide. And then we can take one example to understand this. So starting with the two electron pairs example. If two electron pairs are in a molecule, these both will be bond pair. There is no possibility of lone pair if there are a total two electron pairs. Then shape of that molecule will always be linear. Example is BeH2, BeF2, carbon dioxide. All these they have linear geometry because in their Lewis structure there are only two bond pairs. So to know that bond pairs are there, how many are there, lone pairs are there, how many are there, we need to draw first of all the Lewis structure. Now after the two electron pairs, next I am taking is the three electron pairs. If three electron pairs are there and all three if they are bond pairs and no lone pair is there, geometry will be regular symmetrical geometry, and that is triangular planar geometry. Example is BF3, AlCl3, SO3. But if there are 3 electron pairs, we have one more possibility that there can be 2 bond pairs and 1 lone pair also. So if lone pair will come, geometry will become little distorted from triangular planar and it will become bent, or we'll say inverted V shape. Bent, or the shape will be inverted V shape. Example is O3, SO2. These examples we can take. So now I'm taking this example of BH3 or BF3 example we can take, and we can see that there are 3 bond pairs here. Then I'm taking the example of O3 to know that one lone pair is coming. So how from this regular geometry the shape will become distorted. BH3 example, combining with the 3 hydrogen atoms. So draw the Lewis structure to understand this. This boron has 3 electrons in the last shell. Now this is exception to octahedral, we know. So 3 bond pairs are formed, no lone pair is left here. 3 bond pairs are there, no lone pair, shape is triangular planar. Triangular planar shape is like this. This B is here and towards a corner of a triangle here, the 3 hydrogen atoms they will link. So this kind of geometry is triangular planar geometry, and angle here is 120 degree. All these angles, they are 120 degree. But if we take the example of O3, in O3 we have here double bond, and this side we have a coordinate bond, and after that one lone pair is left here. From Lewis structure we'll come to know one lone pair is left here. We count that double bond also has 1 bond pair and this also has 1 bond pair. So how many bond pairs are here? 2 bond pairs and 1 is a lone pair here. 2 bond pair and 1 lone pair. So if total, like we have 3 electron pairs and all these will be the bond pairs, shape is like this. But now out of these 3 bond pairs, 1 will become a lone pair. So if 1 will become a lone pair, these hydrogen atoms are writing like this, 2 bond pairs, and this is example of ozone. And here we will have a lone pair that will come here. So it is triangular planar, this is triangular planar, but little distorted because of lone pair repulsion will not be same. So it is pushing these bond pairs because repulsion is more. So these 2 oxygen atoms will come little close to each other. So angle will decrease from 120 degree. So this kind of shape is inverted V is formed, or it will bend little bit because the presence of lone pair repulsion is more. So this shape is called bent shape, or this is known as inverted V shape. Now after this we have, if there are 4 electron pairs and all 4 are bond pairs, no lone pair is there, shape is regular, no distortion, it is tetrahedral shape. Example CH4 we can take, and we know carbon combines with 4 hydrogen atoms, uses all its 4 electrons, so there is no lone pair left on the carbon, there are 4 bond pairs. So this kind of geometry that it is forming is tetrahedral. Angle here is 109.5 degree, or we can write 28 minutes in place of 5 degree. This is the shape, tetrahedral shape, if there are 4 bond pairs. But if there are 4 electron pairs, we can have a possibility that 3 can be bond pairs, 1 can be lone pair. So shape from tetrahedral will be little distorted, and that shape is called pyramidal shape. Example is NH3. Now out of these 4, 1 will become a lone pair. Nitrogen combines with 3 hydrogens and 1 lone pair is left on nitrogen. So here a lone pair will come, because of which it is repelling these bond pairs, and bond pairs they come close and angle will decrease from 109.5 degree to 107 degree. So this shape will be little distorted from the tetrahedral, and if 1 lone pair will come in this, we'll call this shape as a pyramidal shape. But now one more possibility also we have here, when 4 electron pairs are there, that 2 can be bond pair and 1 can be the lone pair here in this case. 2 bond pair and 2 lone pairs can be there. In 4 electron pairs, 2 bond pair, and if 2 lone pairs are there, then also the shape is bent, or this is called inverted V shape. Example is water. In water, O combines with 2 hydrogen atoms, and after that 2 lone pairs are left on oxygen. So 2 lone pairs are there on this, because of which repulsion will increase, and the 2 bond pairs will come still more close to each other, and now the angle will be 104.5 degree. So this one will have a distorted geometry. Next, if there are 5 electron pairs, all 5 are bond pairs, no lone pair is there, then the geometry is regular, and that is called trigonal bipyramidal geometry. This table we have to learn only, that if these many bond pairs are there, what will be the geometry, these many bond pairs, these many lone pairs are there, what will the geometry, so that we have to learn only. So if there are 5 bond pairs and no lone pair is there, geometry is trigonal bipyramidal. Example we can take is PCl5. Phosphorus combines with the 5Cl with the bond pairs. 3Cl are linking with the phosphorus through the corners of equilateral triangle. Through the corners of equilateral triangle, they are linking with the phosphorus like this. But the 2Cl, they are linking with the phosphorus from one above the plane, one below the plane. So the angles here are different. These are making an angle of 120 degree, but above the plane and below the plane the angle is 90 degree. So this kind of geometry is called trigonal bipyramidal geometry. But if 5 electron pairs are there and there are 4 bond pairs and one is a lone pair here, then the shape is called a seesaw shape. Example is SF4. Now see, sulfur has 6 electrons in its last shell. 4 this is used to combine with the F, and 2 electrons are left, that is 1 lone pair is left on the sulfur. So total there are 5 only electron pairs. Out of these 4 will become the bond pair and 1 will become the lone pair. So now in this shape there is some distortion, and that distortion will be like when we are introducing the lone pairs in this geometry. Remember that will always introduce towards the corner of an equilateral triangle, never above or below a plane. So this one, this side, I'm making a lone pair, combining with the F through these corners of triangle, one F above the plane and one from below the plane like this. So if we tilt this, it will look like a seesaw only. Just see, if I'm tilting it, it looks like a seesaw is formed here. So that is why this kind of geometry is known as seesaw geometry. Now one more possibility we have here. If there are 3 bond pairs and 2 are lone pair, then that shape is called a T shape. Example I'm taking is ClF3 here. Cl has 7 electrons in its last shell. Out of the 7 electrons, it has used the 3 electrons to combine with the fluorine, so 3 bond pairs are there. Now 4 electrons are left with the Cl, which will make 2 lone pair. That means there are 3 bond pair and 2 lone pairs here. In this regular geometry only, if you have to introduce the lone pairs, I said only towards the corner of a triangle we will introduce a lone pair. So these 2 sides I am making a lone pair, and above, below the plane and this side we will have the F. So this kind of shape is called a T shape. Just see, if I am just rotating this, this becomes like a T only. So remember, the shape is because of the bond pairs, not because of the lone pairs. So this kind of geometry is a T-shaped geometry. But we have one more possibility in the 5 electron pairs. 2 can be bond pairs and 3 can be lone pair. This shape is linear, or we can say diagonal, linear or diagonal. Example here is XeF2. Xenon has 8 electrons in its last shell. Out of 8 electrons, it has used the 2 electrons to combine with the fluorine above and below the plane. And after using 2 electrons out of the 8, 6 electrons are left with xenon. These 6 electrons will form the 3 lone pair, which will be towards the corner of this equilateral triangle. So this shape is a linear shape or diagonal shape. So if we have 5 electron pairs, we have these kind of possibilities. This is a regular geometry and these 3 are the distorted geometries. One more example we have to cover up here. When there are 6 electron pairs, out of 6 electron pairs, 6 are the bond pairs and no lone pair is there, then the geometry of that molecule is octahedral. Example is SF6. Now sulfur here has 6 electrons in the last shell. All 6 electrons are used to combine with the 6 fluorine atoms, and octahedral means 4 fluorine are combining with sulfur from the 4 corners of a square, one above the plane and one from below the plane, like this. This kind of geometry is octahedral, where all angles are equal to 90 degree. But when there are 6 electron pairs, we have one possibility here that 5 can be the bond pairs, 1 can be a lone pair. So now in this geometry there will be some distortion. Lone pairs in this case we will introduce only above or below the plane. While in case of the 5 electron pairs, I said that lone pairs will not come above and below, they will come only towards the corner of equilateral triangle. But in this case, if we have to introduce this lone pair, that lone pair will come only above or below the plane. For this case, I am taking the example of ClF5. Cl has 7 electrons in its last shell. It is using 5 electrons to combine with the fluorine. 4 towards a corner of square, 1 let's say above the plane. And out of 5 electrons which are used with this thing fluorine, 7 electrons were there with Cl. So 2 electrons are left, that means 1 is a lone pair. That can be above the plane or below the plane, like this. So from this shape there will be little distortion now because of the lone pair. Name of this geometry is square pyramidal geometry. This is called square pyramidal geometry. Now one more possibility have, there can be 4 bond pairs and there can be 2 lone pairs also. So if 2 lone pairs are there, now we are clear that they will be only above or below the plane. So both these, they will become the lone pairs. This kind of geometry, and this is called square planar geometry. This is a square planar geometry. Example I am taking is XeF4. Xe has 8 electrons in its last shell. It has used 4 to combine with the 4 fluorine, and 4 electrons are left with xenon, which are forming the 2 lone pairs, one above and one below the plane. So this is a table for the Vesper theory to know the shapes of the molecules till 6 electron pairs. Now this is that we have to learn, but if some other examples we will get, then there is one hint here to find out the shape of any molecule, that is calculation of total number of electron pairs, bond pairs and lone pairs. We have to calculate these, and if we know this thing, we can predict the shape of the molecule or ion, and predicting the shapes of the molecules and ions. This method is find out, first of all, first step is total number of electron pairs around the central atom. How we can calculate the total number of electron pairs around central atom? This is equal to half of the number of valence electrons of central atom. To this we will add number of atoms linked by single bond to central atom, and those atoms will link by the single bond which are monovalent in nature, like the hydrogen, fluorine, but not oxygen, because oxygen is divalent in nature. To this, if we have negative ion, if ion example is there, if negative ion is there, Then what we have to do, add number of electrons equal to the negative charge. If one negative charge, one electron. If two negative charge, two electrons to the valence electron of central atom. To valence electron central atom, we will add the electron equal to the charge. But if there is a positive ion, so those many number of electrons we will remove. Subtract number of electrons equal to the positive charge from the valence electrons of central atom. Now after this, the second step here is, from this is electron pair. How many bond pairs are there? How we'll come to know? Number of bond pairs are equal to number of atoms linked to central atom by single bonds. So this number that we'll write here, this will be equal to number of bond pairs. Now number of lone pairs. We have calculated the number of electron pairs. We have calculated the number of bond pairs. Subtract the two will give us the number of lone pairs. So electron pairs minus the bond pairs is equal to number of lone pairs. So now if we know the bond pair, we know the lone pair. If we remember that table of Vesper theory, we can predict the shape of the molecules. Now using this, I'm taking some examples where we can use this method. Finding out the geometry of any molecule or ion. Example, what is the geometry of Cl F3, Br F5, NH2 minus, H3O plus? Without drawing the Lewis structures to find out the bond pair and lone pair, if we have to tell, then we will take the help of this method. That is, Cl has how many electrons in its last shell? There are 7 valence electrons. So to find out the first step, electron pairs of central atom of Cl equal to half of valence electrons of central atom. Cl has 7. Fluorine combines with the Cl by the single bond. So how many fluorine are there? 3. So 7 plus 3, 10. 10 divided by 2 is 5. 5 electron pairs are there. Second step is how many bond pairs are there? Bond pairs are equal to these atoms which are linking through a single bond. That is 3. So how many lone pairs are there? Electron pair minus the bond pair, that is equal to 2. So if there are 3 bond pair and 2 lone pairs, first of all learn the geometry, that is the regular geometry. 3 and 2 means 5 electron pair. If 5 electron pairs are there and all these are bond pairs, geometry will be like this. That is the trigonal bipyramidal geometry. But now here we have 2 lone pairs. So in this regular geometry, 2 lone pairs we have to introduce, that is towards the corner of equilateral triangle. Only the lone pairs will go. So this kind of the shape we are getting. Here is Cl, here is F, F and F. So which kind of shape this has? That is the T shape. So like this we can find out the geometry of these molecules. Now come to Br F5. Electron pairs of Br are equal to half of, Br is halogen. Halogens, they have 7 electrons in last shell, combining with the 5 monovalent atoms fluorine. So this is coming out to be equal to 6. Bond pairs are equal to monovalent atoms 5 and lone pairs are 6 minus 5 is equal to 1. So 5 bond pairs and 1 lone pair. Electron pairs are 6. If all 6 are bond pairs, regular geometry will be like this, that is octahedral. But now in this we have to introduce 1 lone pair that will be above the plane or below the plane. So this means here we have Br, F, F, F and F here. This kind of shape with 5 bond pair and 1 lone pair is square pyramidal geometry. This has a square pyramidal geometry. Now NH2 minus, electron pairs of nitrogen here. Half of nitrogen has 5 electrons in its last shell, but there's 1 negative charge, so we will add 1 here to this. 5 plus 1 means 6, plus monovalent atoms are 2 in number. 8 divided by 2 is 4. Bond pairs are equal to monovalent atoms, that is 2. lone pairs are equal to 4 minus 2, that is equal to 2. So total 4 electron pairs are there. That means this geometry will be, if 4 bond pairs are there, it is the tetrahedral like this. But now there are 2 lone pairs in this regular geometry. So this one and this one I'm making a lone pair. So here hydrogen and hydrogen will come. Put this thing in a bracket and write the charge here. This is NH2. This shape is bent shape or inverted V shape. Next one is H3O plus. In H3O plus, central atom here we are taking is the oxygen. So valence electrons of O are equal to 6 in number. Electron pairs are equal to half of 6 and this plus charge. That means 1 we have to remove from this. So we are taking 5 here. Plus it is combining with the 3 hydrogen atoms. So A divided by 2 is 4 coming out to be here. Electron pairs are 4. Out of this bond pairs are equal to 3. Lone pair is 4 minus 3 is equal to 1. So if total electron pairs are 4, geometry will be tetrahedral like this. Oxygen is here. But now here 1 is lone pair. If 1 is a lone pair, let's see, make this as a lone pair. So what will be here? Hydrogen, hydrogen, hydrogen. Put this thing in a bracket, write plus charge here. So when there are 3 bond pairs and 1 lone pair, geometry is called pyramidal geometry. So it will be easy. If we'll do the calculation like this, we can find out the geometry of any kind of the molecule or ion. But the table we should know first of all that what will be the geometry of the molecular ion if these many bond pairs are there and these many lone pairs are there. So this is about the Vesper theory.